Hello, physics class. We're ready to work on changes of state and laws of thermodynamics in this particular section of the chapter. Now, there had been a question on a couple of the questions in the practice problems 9 and 10. So what I'm going to do is I'm going to address that when we get a little bit further on in the lesson because it overlaps a little bit about what we're going to talk about today. But the most common states of matter that we're used to seeing around us are solids, liquids, and gases. Yes, I know in the universe you've got plasma, and plasma is really more, but as far as what we deal with on a day-to-day basis, we're talking about solids, liquids, and gases. And so this is where we're working on our understanding today. When energy increases, okay, there's two things that can happen. Okay, you've got a material and it is gaining thermal energy. One of two things can happen. It's either going to get warmer, in other words, an increased temperature, or that energy is going to be used to change states. So the energy as it is absorbed can be used to change it from a solid to a liquid to a gas, or if the energy is being removed, it can go the other direction. So here is an example of what happens as far as energy being added into some ice. And as the energy is added into the ice, what happens with the temperature and what happens with the state changes. Okay, so what's happening for a while is if you have ice and you start adding heat energy and the ice is cold ice. Okay, you can have colder ice and you can have warmer ice. Okay, if you set your freezer at different temperatures, you can make colder ice, and then if you set it a little higher, your ice isn't quite as cold. So you have different temperatures of ice, but you start adding heat energy to the ice. What will happen is that ice will get to be warmer and warmer and warmer ice until it hits a certain temperature, and that temperature is what's known as the melting point. So after you make warmer and warmer and warmer ice until you get to 0 degrees Celsius or 273 Kelvin, at that point, when you begin to add heat energy to that ice, something different happens. Okay, and I am giving credit to who credit is due for these things. When you start adding more and more and more heat energy at a certain point, melting begins to happen. Okay, you get a certain temperature and melting happens. That ice and that water that are both included in this, okay, that ice and that water right here are the same temperature because it's gotten to that warm enough ice stage that the energy that's continuing to be added in actually begins to be used for changing it into water. Okay, same thing in the reverse. If you're having energy taken out, okay, and so the surrounding air or the surroundings are colder, okay, what happens is you get to the freezing point, which is the same point as the melting point as far as temperature goes, and as more energy is taken out, it begins to change state and freeze. So freezing and melting are happening at the same temperature, but the surrounding temperature is the same. It's just a matter of, is there being heat added in the case of melting or heat taken out in the case of freezing. Okay, so let's get back to our chart here. So this is what's happening. You have ice that's getting warmer, and then you have a mixture of ice and water at that same temperature. If it's a closed, isolated system. If it's not, we have other things to consider, but we're just thinking about a closed system where you've got ice and water and you've got some heat energy that's being added. So we add the heat energy, and for a while, all of the heat energy is going to change that ice into water. Once it's all changed over into water, then the water starts to get hotter and hotter and hotter. The temperature rises and rises and rises, and this is all water. Once you get to a certain temperature, that's known as the boiling point, all of the heat energy, instead of going to change it to being hotter and hotter and hotter water, all that heat energy is going to change state and change it into boiling. It's changing it into the gas state. And the reason something boils is that water that's inside the pot is turning into the gas state, but it's turning into the gas state down close to where the heat's being added, so it bubbles up and comes out, and that's what boiling is all about. It's those gas bubbles where it's really just water in the gas state that has to go somewhere, and it is less dense than the water itself, so the only place it has is to go up. So you've got boiling happening. The boiling point is when that water has gotten enough heat energy in it that it's up to 100 degrees Celsius or 373 Kelvin, and then heat energy continues to be added, and that is used then for a change in state, and it becomes in the vapor state as well. Now, if it is a closed and isolated system, what happens is that if there's more heat energy added after it all turns into water vapor, it would get to be hotter and hotter water vapor. Okay, now in our real world, you usually have situations where you're not a closed isolated system, so that water vapor can hang in the air. The water vapor itself can cool, but we're talking about in a closed isolated system as far as how this is happening. So I had said this a couple times, but please write it down. For ice, the melting point is 0, same as the freezing point, or 273 Kelvin. Okay, remember there's a 273 for our conversions. Okay, 100 degrees Celsius for water to boil, or 373 Kelvin. Now, water and other substances have different boiling and melting points, but for the sake of simplicity, we're using mostly water in terms of that. Now, if there were another type of substance, that boiling or that melting or boiling point would have to be given to you. And you can think about your meltable metals when you can think about melting as well, or you can even think about boiling metals. Okay, you can think about changing over into other phases with some of those things. Okay, so there's still heat energy. Remember, heat energy, we said, is different than temperature. So Q we had used as MC delta T when the temperature was changing. But when the temperature isn't changing and you're still adding heat energy, we have another number. Remember, we had C was the specific heat, and it came from a chart, and it's substance specific. You also have substance specific heat energy that's required to make a change of state. So for example, HF is the heat of fusion, and you would be able to find that in a chart on page 287 for some common materials. Or if in your test, you'll be given the heat of fusion or the heat of vaporization if you need it for a specific problem. So heat of fusion is the amount of heat that's needed to melt or to liquefy a specific substance. Okay, so melting, in other words, solid to liquid, you have a certain amount of heat that needs to go in, and the heat of vaporization is the heat that that's the amount to make liquid turn into gas or vaporize that for 1 kilogram of a substance. So when you multiply that times the mass, then it gives you the total energy that's needed. So these numbers, like I said, you'll find them in a chart, and they are substance specific. And somebody figured that out a long time ago. Okay, so let's go through a process here. This is going to combine information that you had yesterday, or not yesterday, but the last time we had class. And it's going to combine it with our new information about state changes. Okay, so you have 500 grams of ice at negative 10 degrees Celsius, and we want to know how much heat is needed to melt the ice. Well, two things have to happen. First of all, that ice has to heat up to 0 degrees Celsius. It has to heat up to the to that specific temperature that's needed for melting, the melting point. So we're going to need to put energy into it to get it up to temperature first, MC delta T. So we have our specific heat of ice, and strangely enough, the specific heat of ice is different than the specific heat of water. It takes a different amount of energy to heat ice than it does to heat water, which I find very interesting. The water's a little bit more spread out than, so it just takes a different amount of heat. But you'll find that in the chart. So when you're looking for the chart, make sure that you differentiate between H2O in the ice state and the water state. So specific heat of ice is 2060. 0.5 is the mass of the ice. 500 grams, remember you have to make it into kilograms first. We'll move the decimal 3 places, 0.5. Change in temperature. The temperature later, which is 0, minus the temperature earlier, which is negative 10. Later minus earlier. So we're really taking 10 times 5, so 5 times 2060, 10,300 joules before it has even begun to melt. It has been brought up to temperature now. So now this piece of ice is now brought up to temperature and it's ready to melt. And at that point, more heat energy needs to be added in. So in order for the ice to melt, the energy needed is the mass times the heat of fusion. Okay, the heat of fusion once again would be found in a table that mentions the heat of fusion numbers. And our heat of fusion number for that is 3.34 times 10 to the 5th. So you multiply 0.5 times 3.34 times 10 to the 5th. And we get 167,000 joules. So it takes this amount of energy to bring it to warm up the ice and this amount of energy to change it into its new state. So altogether, to take it from here to being all water, you need both of those things to happen. So we need to add them. When you add them, you have a total amount of energy that it takes to get this piece of ice up to 0 and then melted. Interestingly enough, once it's melted, as long as it's just that ice cube and the heat being put into it, once it's melted, it's all water at 0 degrees Celsius. Okay? It's all water at the freezing point, 273 Kelvin. All right, so two things happening. The ice brought up to temperature, and then the ice melting. Okay, we have a slightly more complicated example for you to take a look at, and then you're going to work on problems 11 to 14. And that really is all of them. I have sent you your study guide, so you need to work on that afterwards. All of it due in a week on next Tuesday. Okay, so we have 250 grams of a mystery substance. Okay, and it's at its melting point, some kind of mystery metal. And its melting point is 520 degrees Celsius. Okay, so very, very hot melting point. It's dropped into 300 grams of water that's at 20 degrees Celsius. The heat of fusion for the substance is 4.3 times 10 to the 4th. So this substance, okay, is in its liquid form. Okay, think about like liquid gold, and it's being poured into the water, and the water is cool enough that that gold becomes a solid. So it's very high temperature, whatever this is, this substance, it's in a liquid state. And so the heat is going to be coming out of that substance and going into the water. So it's reversing the process. It's not melting in this case, but it is turning into the solid state. So we have two things to consider: what the temperature of the water will be as soon as the substance becomes solid, and then when they become into thermal equilibrium, what the temperature is. So you can picture you've got a giant vat of water, you put in the molten gold or the molten whatever this is, the liquid metal, it gets solid, and then it heats up the water until the water is actually brought up to temperature. So let's find out what happened. Let's find out if it actually would make the water boil, because there's that too. So first thing we need to do is we need to think about the temperature of the water when the substance becomes solid. So we have, first of all, to figure out how much heat energy came out of the mystery substance to turn it solid. The heat of fusion for the substance is 4.3 times 10 to the fourth. So that's the amount of heat needed for 1 kilogram to change its state. 250 grams is 0.25 kilograms. Mass times the heat of fusion. And so that part means that 10,750 joules of heat was transferred while it was turning into its solid state. Well, what did that heat that was transferred into the water, what did it do to the water? The water was already in its liquid state. So what happened was that heat that was transferred into the water is used to make the water warmer. So we have a second thing happening. The energy, the 10,750, is being put into the water, mc delta T, mass times the specific heat times the change in temperature. So the mass of the water, 3 kilograms, 0.3 kilograms, moving over 3. The specific heat of the water from the chart, delta T, the later temperature minus the earlier temperature. It says the earlier temperature of the water was 20 degrees Celsius. But the final temperature is what we're looking for. So here's our amount of energy. Here's our mass. Here's the specific heat of liquid water. Final temperature minus earlier temperature. And we need to use some algebra skills. Multiply that out. Then distribute. Or you can even divide both sides by 1254, whichever your preferred method is of getting your solution. So our final temperature, 28.6, is our final temperature of the water. Now that's just simply when it put the how much energy it was taken to change the state into a solid, and then it heated the water up that much. But that's not done, because at that point you have this 520 degrees Celsius blob of metal that's sitting in the water, and it's still 520 degrees Celsius. It just happens to have become a solid instead of a liquid. So here's where it goes into yesterday's problem for question 10 is very similar to part B of this problem. So after you've heard this, I want you to go back and give question 9 and 10 another try, okay? Because this part is kind of like question 10. So we've got the water at 28.6 degrees Celsius. So this is our new starting temperature of the water. And the starting temperature of this mystery substance as a solid is 520 degrees Celsius. And this is where we were the last lesson. So we have a change in energy for the one substance plus the change in energy for the other one has to equal 0. This is an mc delta T and an mc delta T. But keep in mind the final temperature for both, because it's coming into equilibrium, has to be the same. So our final temperature is the same. So when I do MC delta T here, here's my mystery substance. C, the specific heat of the substance, you have to be given that somewhere, either from a table or I just gave it to you, is 370. The final temperature minus the starting temperature. Okay, when I add that to the mass of the water, which is still 0.3, it hasn't changed mass. Here's our specific heat of the water, which is the same, the liquid water. Final temperature minus starting temperature for this phase of the problem. Because remember, the water has already been heated up by the state change for the substance. Okay, but this is where you would figure out, and this is how you would do problem 10. You would have a problem that's set up like this. Then you need to use some algebra. You need to solve this out. So we multiply these together. We multiply these together. Then you have to distribute and combine like terms, which I know you are able to do. You might want to pause it because a lot of you like to do the problem and then make sure you're right. So please make sure you can do this. Put our like terms together. Add the things that are subtracted to both sides. And then divide out. And we get that our final temperature for both the chunk of metal, or whatever the substance is, that chunk, and the water is 62.4 degrees Celsius. It is still below the boiling point of water, so that's good. So there's another example of how water is just really, really good as far as being a coolant, because that water got warm, but it didn't get to the point where it's boiling, which would be a problem. So it is good at taking something that's very, very hot. This is over 500, when just 100 is the boiling point of water. So took something very, very hot and brought it down to a reasonable temperature in that. So that's our thrust of our information today. As far as question 9, because that had been asked about as well, your hint for question 9, actually 9 is more like this. 10, you are being asked to find specific heat. So in 10, you would have all the information, but specific heat, a C, would be left as a variable in here. So question 9 is more like that. Sorry about that. Okay, from part B, this is like question 9, and question 10 is if you had a variable left here, but you knew the final temperature, so you'd have a number put in these two spots. Okay, so once again, question 9 is like this. Question 10 is more like there's a variable here, and you have a number here and here, and you would do your algebra that way. Okay, so go back, for the person that was your question, please go back and give questions 9 and 10 another try. And then let me know again, and I'll make a video specifically explaining those. But I need to know if that cleared up enough. All right, fair enough. And that's it for today. You're going to need to work on questions 11 to 14 and give me an update as far as where you stand on those things. And that's it. So have a really good, blessed day.